In this presentation, we're going to talk about the central limit theorem. Essentially, I'm going to describe mathematically what it means, and then I'm going to do a computation example. So the central limit theorem is essentially a way for us to handle variability in data, essentially by averaging the number of observations. So for example, in hypothesis testing, what we do is we compare averages of a set of observations to a certain threshold, and that kind of gives us an idea of what's going on. So let me show you what it looks like first mathematically. So again, the central limit theorem is just an average of the number of observations. So as you can see here mathematically, we have x bar, which is our average value of our random variable x, is equal to 1 over n, where n is sort of our number of observations, our number of samples, and basically what we do is we sum all of the observations and we divide them by n, which, I mean, this is just sort of a really fancy way for you to see what average looks like in mathematical terms. So there are a couple key things you need to know. First is that, or assumptions that we make. The first one is that all of our values of x are independent of each other. So for example, the temperature that we collect in the beginning of August is independent of the temperature or the observation that we collect in, the second day of August. And because of that, we have a mean, again, that we can denote as mu, and then we have a variance, again, that we can denote as sigma squared. So what happens when we do something like hypothesis testing is what we're trying to do is we're essentially trying to find the probability for our average observations being less than or equal to some arbitrary value of x. And this is sort of hard to understand, but what we can do is we can use the central limit theorem to sort of allow us to ask these questions in hypothesis testing and actually get an answer. And the reason, again, is because there's I shouldn't say the reason again, but essentially what happens is that in our central limit theorem, we assume that an average of x, so our x bar, is approximately normal. And the reason is that when we have a really large number of observations, the distribution of that average becomes more normal. So actually what we recommend as statisticians in engineering is to get as many observations as possible, because the more observations there are, the more likely that normality is going to hold, and so we're really going to get an idea of what the data is telling us and what we can extrapolate and compare that data to. And that's what hypothesis testing is all about. And because of this assumption that we can make using the central limit theorem, we can essentially use some of our sample statistics. Here we can say that the mean of x bar, so the mean of our average, is, in our case, just equal to the mean. However, when we use the variance, we're going to use the variance for our average, but divide it by the number of observations that we have. And similarly, because the standard deviation is dependent upon the variance, we have to do the square root, where again we are dividing the variance by the number of samples and then square rooting it in order to get, again, this is our standard deviation. So let's do an example. So let's say we have some random variable, which we'll call x1, and it has a mean of 0.5 and a variance of 0.1, and we know that it has a total of 8 observations. And let's say we're wanting to find the probability of x bar being less than 0.75. So the first thing we need to do is we sort of, just for our own purposes as we practice what the central limit theorem means, is we're just going to transform x bar into that funky equation I showed you earlier, which is basically just a complex form of the average. This is 8, starts at 1, and r of some observation xi. So in order to find what that probability is, we just basically go back to some of the things we've already been doing in the past. But now we're going to use terms of the central limit theorem. So instead of using mu, we're going to use mu of x bar. We're going to use variance of x bar. So what we need to do is solve for those values. So again, we already know that the mean is the same. So remember, mean of x bar is equal to the mean, which is 0.5. And our variance of x bar is our variance divided by the number of observations. So in our case, it's 0.1 divided by 8, because remember we had 8 observations here. And then we can go in and we actually can get the standard deviation, which is just this, and that's equal to 0.1118. So then the next thing we do is when we're trying to solve for probability, what do we have to do? We have to standardize it. So in order to standardize, remember we have to convert it into that z function. So z, again, is equal to the mean minus, is equal to our x, in our case x bar, minus the mean divided by the standard deviation. So in our case, we get z, probability of z being less than or equal to, in our case, z, we'll call it x bar, which is that value. And so p is equal to z less than or equal to 0.75 minus 0.5 divided by 0.1118. And then all we do is we go and use our norm sdist function in Excel, as you can see here. And we essentially just plug that, so the value that we calculate for this gets plugged in there, and what we ultimately find is a probability of 0.99. Let me rewrite that so you can see it better. Ta-da! So as you can see, when we use the central limit theorem, we're essentially just averaging our observations and using that in order to calculate probabilities. And to calculate probabilities, again, we have to standardize, because by standardizing, we actually have a better or an easier method to do it. If we don't want to standardize, you don't have to standardize. We could have just solved for it in Excel because of that option. But again, we usually try to standardize this stuff because it is easier to work with. So I hope you have a better understanding of what the central limit theorem is and ultimately how to do a computation using it. Thanks.